Exascale supercomputing is a massive leap forward in computational power. To set it in context, when the petaflop barrier was broken, that was in 2008, and it took 14 years for us to achieve 1,000 times that computational power. The types of applications for exascale will have significant impact on the human experience, whether that's solving our most pressing challenges in climate science, in health and life sciences, in clean energy solutions, in making transportation solutions safer and more efficient. So the massive increase in computational power and in speed is not just speed for speed's sake, it's speed for human's sake. It's a great time to come do cool stuff with smart people to make the world better.
So I've been coming to supercomputing since 2005. I'm glad to be back here after a 2-year absence. It's good to see people again. It's a really important show for us because it showcases all the new technology that our company depends on.
We've actually been attending SC for long time. I think the community is kind of getting back together. It's awesome. I think we have done a lot interactively for a long time.
There are a lot of emerging technologies that are kind of hard to evaluate strictly from the promotional materials, so getting in and really asking questions while simultaneously talking to my peers and people at other institutions so that there's that wider context it's been helping guide some of the strategic information that I'm looking for what do we do next.
As part of the interconnected science ecosystem, I'm trying to connect all the different scientific instruments with edge devices, with high-performance computing, and this is a great place to come and talk with people about scientific workflows and how we might make this come to fruition.
I think it's fairly well understood in the industry that as you increase data rates through these limited number of copper pins, the power consumed in driving that is now becoming greater than the power available to do the computing. Now, instead of the I/O exiting through these copper pins, and you can see there's thousands of them, and it's becoming more and more difficult to exit the kind of bandwidth you need out of the package. We enable all the I/O now to happen through fiber optic communication rather than through copper.
The big shift this year, what we've noticed is a adoption of direct liquid cooling in enterprise applications. As some chips are launched from the major chip manufacturers that actually require liquid cooling, there's been more data centers adopting the technology so they can run the latest and greatest chips. So in the past, we used to work with a lot of universities and research centers and groups that were doing probably more supercompute products. We still work with those groups and they're still deploying a lot of liquid, but this year the story has been enterprise adoption. So high frequency traders, automotive manufacturers, companies looking to leverage HPC more in an enterprise class system.
It's really fun to come to supercomputing every year and look at what technologies and innovations, what software, what programming models are going to change the way that supercomputing is done years from now. We're seeing programming models like SPAC being used to enable users to package up an application and run it on different architectures. That type of work done by Lawrence Livermore and AWS is really groundbreaking innovation. Machine learning is going to accelerate HPC in a way we've never seen before. And we see that today with physics-informed neural networks and with large language models, and we're just going to see that explode over the next few years.
So when I look at everything that's happening today here in Dallas, I'm really excited about innovation and the technologies that are being brought to market. You see innovation on the CPU side, the GPU side, the interconnect, cooling, power delivery, but also innovation in the software stacks and how people are adding even more value through standardization. And the last thing is everybody's more interested in driving that HPC growth than ever.
They say out of sight, out of mind. SC22 does the opposite. It puts everything right in front of you, and sometimes things just click that didn't click before because you're seeing everybody. Everybody needs HPC for something as far as I can tell.
I think that a lot of our assumptions about how to handle computation have been built on Moore's Law capped out. But now we've got this power constraint coming into play. So we've been able to have a lot of inefficiency. We've been able to really just sprint as far forward as we can, as fast as we can. I think in 10 years there's going to need to be more consideration so that we actually use the power that we've got to advance things as best we can.
For the future kids that are coming up, behind me, there's a whole new world of science and how they're going to do science, and it's really going to start blending together computing and experimental science. The ones that are coming up behind me, they're going to be thinking about science in a completely different way. What instruments are available, what compute is available, how can I use both of these at the same time to do an experiment that I couldn't do 10 years ago.
I'm really excited by the new generation of HPC and AI developers, mostly because they are not encumbered by the old way of thinking, right? They're not thinking about, I need to have time at a supercomputer, or they're not restricted by constraints of the past. They're really thinking about what's the next generation of model I need to develop. They don't care where it runs, how it runs. And I think that really allows innovation to happen faster because they're not taking some of those boundaries that used to exist before. And they're like, okay, if the compute is in cloud, so be it. If I have to go to the next generation, so be it. With a mindset that is very different. They don't care about belonging to certain groups or having access to a particular infrastructure. They're really about how quickly can I get to the next generation. And that is really exciting.
We have to sort of invert the way we think about data centers. My entire career, managing electricity was very important, and we would want 4 nines or 5 nines of electricity availability. We're not going to get that with renewables. So instead of having the grid adapt to what the data center wants, we're going to have the data center adapt to what the grid's got.
As we look forward to the future, data is becoming the challenge for all of us. If you look at simulation workloads, if you look at AI, machine learning, and high-performance data analytics workloads, those workloads are more complex than they have been before. The types of questions we're asking of them are more complex, and the data that drives them is continuing to grow. So as we move forward, it's important that we understand that the CPU, the GPU is going to get closer to the network, and we have to have creative high-performance solutions that not only enable that, but are also open and interoperable with the systems and the ecosystems that our customers have deployed in their environments.
It's much more about the software and the people than the hardware, and we've got to keep developing the talent. I really want to see more women and underrepresented minorities at this conference and writing papers and helping to support researchers in this field.
The advancement of scientific progress for humanity, it just makes life better for all of us. It's not just predicting the weather, making better airplanes, or discovering new drugs. That makes life better for all of us. You can't beat that. Let's put our technology to good use.